All right. Good afternoon, everyone. Welcome to today's webinar hosted by the SANCOLD Young Professionals Forum. My name is Ashley Kutsia, and I'm the YPF Chair at SANCOLD, currently working at the Department of Water and Sanitation. It is a pleasure to have you all with us today as we explore the topic of upstream dams in South Africa, a subject of growing interest. We are fortunate to have with us three distinguished speakers from ARQ who bring a wealth of knowledge and experience to this discussion. Our first speaker is Beric Robinson, a professional engineer with an impressive 46 years of experience in the tailings field. Beric has been instrumental in the conceptualization, design, construction, and management of over 300 tailings facilities across more than 15 countries. His extensive work includes operations management, auditing, rehabilitation, and closure of these facilities. Beric is also a seasoned lecturer and presenter, having contributed numerous papers and practical innovations that have significantly benefited both clients and employees through his effective and highly innovative solutions. Next, we have Thomas O'Brien, a professional engineer and managing director at ARQ, with 14 years of experience in geotechnical and tailings engineering. Thomas serves as the engineer of record on several facilities, ensuring that mine tailings disposal needs are met. He is an active member of independent tailing review boards for various operations and specializes in geotechnical and tailings investigations, advanced stability and seepage modeling, as well as TSF operation, management, and surveillance. His construction experience on large multidisciplinary sites further enriches his contribution to this industry. Finally, we are joined by Katie O'Brien, a professional engineer with 10 years of experience in geotechnical and tailings engineering. Katie's expertise lie in performing advanced numerical stability assessments on geotechnical scenarios and tailing storage facilities. She is adept at assessing potential liquefaction risks using critical state soil mechanics and has been responsible for numerous geotechnical assessments, investigations, and designs. Her work spans various infrastructure projects, including earth embankment dams, mining infrastructure, and even road upgrades, such as her role as assistant resident engineer for the upgrade of main road P318 Sani Pass. Together, our speakers will delve into the complexities and considerations surrounding upstream dams in South Africa, drawing from their extensive experience and expertise. Before we begin, I would just like to go over a few house rules to ensure the session runs smoothly. The session will be recorded and made available to all registered participants after the event. Your videos and microphones are disabled throughout the presentation to minimize background noise. We will, however, have a questions and answers session at the end of the presentations. And if you have any questions, you can post them in the chat feature, or at the end, just raise your hand and I will give you a chance to speak. Please join me in welcoming our esteemed speakers. Thank you, Beric, Thomas, and Katie, for sharing your insights with us today. The floor is yours.
Good afternoon, Ashley, and thank you for that very flattering introduction. I'm going to share my screen from my side. Can I confirm that everyone can see that?
I can see your screen and I can hear you clearly.
Okay, that's great. Thank you. And then I'm going to hand over to Beric, who will kick things off.
Hi, good afternoon, everyone. Very nice turnout, I see. So the webinar title has got a question, or poses a question, and the purpose of this webinar, well, the intent of this webinar is to try and actually answer that question this afternoon there. But why the question was posed in the first place perhaps requires some sort of context, which I will attempt to provide. And then Thomas and Katie will provide the motivation and substantiation to the answer in their parts of the presentation. And so Thomas is actually running the slides, so I'll ask him to stop on as we go. So yeah, so as said, I'll provide the context. Thomas will give the analytical framework. Katie will then deal with the analytical process, and then I believe there are questions and discussions afterwards. Yeah. So moving on then to the context of the development of tailings dams. So there are three different ways and manners in which a tailings dam or any dam embankment can actually be developed. And that is, the first one is downstream, in which case we start from an inside position, and then the crest and the toe of the wall shifts outwards or downstreams with increasing height, as shown in that little diagram there. And theoretically, this is the most stable form of development that you can achieve. The second approach is actually what we call centerline, where the crest rises vertically whilst the toe shifts outwards. And theoretically, this is slightly less stable because on the upstream side, you have essentially a near vertical face. The third is the subject of our webinar today, and that is called upstream development, where we start from an outside position or downstream position with the toe, and it remains in its original position, and the wall and crest shifts inwards or upstream with increasing height. Theoretically, this is the least stable, as the failure surface, the red line you see there, passes through the contractive, the potentially liquefiable tailings. So upstream dams in South Africa have been developed in this manner, predominantly. Over 99% of them are upstream dams. And the reason for this is that the terrain in which they are developed is predominantly flat, mostly on the high veld and things there. There are no valleys. And so this requires a ring dike dam, a containment wall around the whole impoundment. And these long walls require a lot of material which to form, which the deep underground mines that generate the waste generally provides insufficient waste rock to actually form the ring dike impoundment walls. So then what happened is, in the semi-arid environment, the early pioneers found that the sun dried out the tailings very quickly and made these tailings a suitable material with which to actually raise the dam. And so we didn't need to build impoundment walls with any other material. Then fourthly, the subcontinent is seismically stable. We experience very little tectonic earthquake activity. And then finally, but as a consequence, upstream dam development is far more cost effective. It costs a lot less than other methods. So, but in 120 years of mining and development of tailings dams across hundreds of these dams, we've only had 4 failures of public consequence. And these have all been attributable to actually human activity, or rather the lack thereof, and not due to upstream dam development. So unfortunately, though, South African engineers have never analytically substantiated upstream stability. And this has now placed us on a back foot when it comes to the global developments that have happened in the last few years. So, which is the bad rap that upstream tailings dams have now experiencing. And this came about because in February 2019, the Feijão tailings dam in Brazil, near the town of Brumadinho, failed spectacularly. And that was also on public social media. And so there was a huge public outcry, and the Brazilian politicians moved very quickly to ban upstream tailings dams. The investment agencies and the insurers, to protect investor value and profitability, exerted pressure on the mines to get their act together through the initiation of what is called the Global Tailings Initiative. And a mining body, the ICMM, responded by actually sponsoring the GTI in the development of what has come out as the global industry standard for tailings management, the GISTM. And following the Brazilian political initiative of banning upstream tailings dams, upstream TSFs became the sacrificial lamb in this document and the subsequently updated SANCOLD guidelines for tailings dam stability. So looking at this in a little bit more detail, the GISTM, it does not ban upstream dams outright, but it imposes criteria and standards that are virtually impossible to meet. Particularly, the guide requires a factor of safety of greater than 1.1 when assuming post-liquefaction residual strength. This is the strength that happens after failure. And then putting that into a limit equilibrium analysis. And when you put those two together, it's virtually impossible to achieve that factor of safety requirement. So why did the GISTM assume residual strength and limit equilibrium methods? Well, the guide is motivated by investor and insurer interest rather than the mining company interest, with the former actually attempting to avoid the consequences of failure rather than allowing mines to engineer and manage to avoid failures. So, and the reason that GISTM followed this approach is because historically the mining industry has not looked after or managed its facilities adequately, and are now facing the consequences of it. And furthermore, in 2020, when the GISTM was first drafted, appropriate risk-based analytical tools were considered too complex for general application and were not commercially available. So consequently, the guide followed a sort of a work-to-rule, catch-all, very conservative approach, assuming residual strengths, and the simplistic and traditional but limited limit equilibrium modeling approach as the default. So where does this leave upstream tailings dams? Because no upstream tailings dam can actually meet the GISTM criteria. But does this new standard suddenly make all upstream tailings dams unsafe? So while the hazard and the potential to cause harm exists, the South African record of around 50,000 tailings dam years, with only 4 failures of consequence, demonstrates otherwise. These tailings dams are not unsafe. But condemnation of upstream dams may be largely immaterial globally, but they're hugely significant in South Africa to the economy, where more than 99% of facilities are developed in this manner. And so some mines, South African mines, are in a quandary. They want to comply with the global standards, but historic practice and are in an impossible corner through the unattainable requirements, and with the international guidelines allowing no alternative engineering options. So what can South African mines actually do now? Well, we are suggesting that contrary to the GISTM default approach, rather to adopt a risk-based approach, which is actually allowed indirectly through the draft SANS 10286 Code of Practice. If one recognizes the GISTM work-to-rule approach, which is very prescriptive, it just basically disempowers engineers and owners. It obviates owners and executives and engineers from applying their minds. They just have to follow rules. And so it basically lacks in technical integrity. And so it is not an assured approach to risk management. Alternatively, and is common practice in engineering, a risk-based approach analytically quantifies the likelihood of failure based upon measured and computed information, and it eliminates the need for a conservative catch-all assumptions. But it requires application of a competent mind to the situation, and through that provides the more assured control of risk. That is actually a better approach, in my opinion, than the GISTM default model. And today, analytical tools such as nonlinear deformation analysis incorporated into finite element modeling, using critical state soil mechanics with constitutive models such as NORSAND or PM4 silt, are now commercially available to enable more rigorous engineering to be applied. So finally, after 120 years, South African engineers are, and globally, we are now in a position to actually analytically verify the stability of upstream dams. So that hopefully provides you with some sort of context as to why we are talking about this subject today. And so I'm going to hand over to Thomas now, who will take you through the analytical framework of how we actually go about undertaking the verification of the upstream stability. Thank you, Thomas.
Thanks for that, Beric. Thanks very much. That's a very comprehensive summary, and good afternoon to everyone. Yeah, so I have the task of basically proving what Beric proposes to be possible. So to accomplish that, I'd like to have a brief overview of some of the geotechnical behaviors concerned. For those of you who are geotechnical engineers, I apologize if a lot of it you already know, but for our audience, I believe not everyone will be familiar, and so there's value in it. Then we'll look at the analytical framework proposed by SANS 10286 draft as an analytical approach for assessment. And then we'll look at some of the modeling techniques used, as Beric mentioned, FEM over LEM and so on, to conduct triggering assessments. So let's take a look at some soil behaviors for overall orientation. So as some of you may know, soils and tailings is a soil can behave in a drained or an undrained manner. In drained behavior, soils are either not saturated or deformation is slow enough to allow excess pore water pressures to dissipate. In undrained behaviors, for undrained behavior to manifest, soils must be saturated and they must also be sheared fast enough that excess pore pressures caused during dilation or contraction dissipate. So you might then ask, what are these dilation and contraction terms that I've mentioned? So basically, a dilative soil is a dense soil. That will make more sense later on in the presentation. They generally have a dense particle arrangement, and that tends to drive particles away from each other when the soil is sheared. Conversely, a contractive soil or a loose soil has a loose particle arrangement, which tends to allow particles to move closer to one another when the soil is sheared. So it's helpful to visualize that, having a look at the drained conditions. For a loose material, you'll note sort of diagrammatically there we've represented a loose soil material with the grains not packed very close to each other, but still making contact. And when that soil mass is sheared, the particles are actually allowed or able to move closer to one another. And so in the sample, you get a decrease in height. In the actual tailings dam or soil mass, that would be associated with a decrease in overall volume. And so we get an increase in shear strength with strain. And as mentioned, we get a decrease in volume, a change in volume. Then looking at a dense state, a dense arrangement of particles, as you can see, they're much denser. And when that is sheared in a drained fashion, the particles are forced to climb over one another, out and over one another during the shear deformation. And so you actually experience an increase in volume in the drained state, as you can see there by the green line. And also the shear strength increases and plateaus off at some high value because of the dense arrangement. Then we can look at the undrained behavior, and this is applicable to tailings dams because many of the structural zones are saturated. So again, we start by looking at a loose arrangement of particles or grains. When these are sheared, they want to move closer to one another because of their loose arrangement, but because they are housed within incompressible water, the volume can't change like it does change during drained shear. And so the water actually takes on a pressure because of the will to decrease volume. And that increased pore water pressure actually reduces effective strength, or effective stress, and therefore strength. So this is the typical stress strain behavior of a loose material sheared in an undrained manner, where we have a peak and the strength then dropping down to a residual value. And corresponding with that, we see an increase in pore water pressure. A much more desirable situation is if you have a dense material. When that's sheared in an undrained manner, the particles attempt to climb over one another because it started dense, but they can't climb over one another because the water actually goes into suction, and that suction holds the soil together and makes it very strong. So in that scenario, we see a decrease in pore water pressure, which is associated with an increase in effective stress and therefore strength. So there's no peak and residual. You have finally, when that material does fail, it's quite strong, and it also fails on a plateau. Right, so that's just a recap of those 4 scenarios there. Apologies again, as I mentioned, if you are already experienced geotechnical engineers, that's old news, but perhaps a recap doesn't hurt. And then just to say, the whole stability of these upstream tailings dams really hinges around this one of the 4 permutations, the undrained shear of loose materials, where we have a peak and a residual. So if we are dealing with a loose or a contractive material, you still get different degrees of looseness or strain softening. So I'd like to just elaborate on some principles there. So to say, not all contractive materials are strain softening, and not all strain softening materials are brittle. So here are a series of results from various triaxial tests showing strength versus strain. And this, as you'll see later, is one of the critical state planes, which as I say, I'll explain later, but basically deviatoric stress and mean effective stress. So this sample shown by green, we can see it is contractive, yes, because the stress path bends to the left, but we don't see a great decrease in strength from a peak to a residual. So that material is contractive, but not strain softening. Then looking at the blue sample, which may have been the sample tested may have been constructed slightly looser of critical. This is contractive and strain softening. You can see there is a decrease from the peak to the residual, but it's not brittle. And then the third case, which is contractive, strain softening, and brittle. So as you'll see on the next slide, that last term, brittleness, basically refers to the amount of strength which is lost between the peak and the residual. So the SANCOLD Bulletin 194 has basically classed brittleness in 3 categories. So if you are losing less than 20% of your strength, you are generally not brittle. If you're losing between 20 and 40% of your strength, you are in a moderately brittle scenario. And if you are losing more than 40% strength, you are highly brittle. And that's important to understand because you obviously need to take precautions and perform proper assessments if you're dealing with something that is highly brittle, because there is the potential for liquefaction and it needs to be properly assessed. For interest's sake, for those who don't know or who haven't read the SANCOLD Bulletin 194, this dashed line is actually the stress-strain relationship for a tailing sample tested from the Brumadinho failure, which Beric mentioned in his presentation, and that was, catastrophic liquefaction failure. And you can see that material, when strained beyond its peak strength, really just liquefying and losing almost all of its strength. All right, so you may ask, why are tailings materials subject to liquefaction? Well, the hydraulic deposition of particles results in a loose or normally consolidated particle arrangement or state, and meaningful zones of the material are saturated, and this can behave in an undrained manner. Therefore, if failure occurs, it is often associated with some degree of liquefaction. So diagrammatically again, if that peak strength is insufficient to prevent further movement, and you go off the peak, then your factors of safety or your resistance towards the effect of gravity is going to be much too low, and you could expect a failure. So at this point, I'd like to take a closer look at two types of failure: static liquefaction and dynamic liquefaction. The diagrams that I'm going to show you are not taken from any sort of reference literature. They are my understanding of how these failures progress. They might be interesting to discuss after the webinar. But taking a look at static liquefaction, in my view, you must be in a situation where your drained factor of safety drops or approaches 1. And then because of that, strains occur, movement occurs. The movement occurring basically mobilizes undrained strengths, which are peak undrained strengths at first. Then, if the peak undrained strengths are smaller than the stress or the load, then further movement occurs and residual undrained strengths are mobilized. And as if your material is brittle, the concept that I've just explained, then your residual undrained factor of safety will be much smaller than 1, and you'll have instability and flow failure. Dynamic liquefaction, on the other hand, triggered by a seismic or earthquake, has got a slightly different mechanism, or can have a slightly different mechanism. Your drain factor of safety can be okay, and then a seismic event can be experienced, which causes contraction in your saturated zones, and residual undrained strengths can be mobilized outright without first moving through, without having a movement scenarios, as with the static liquefaction case. So, and then the confinement offered by the unsaturated or unliquefiable zone is insufficient to contain the liquefied material. Your global factor of safety drops below 1, and instability and flow failure can occur. So it's just, in summary, important there to note that in the static liquefaction case, you have failure first through several gates, as I call them, followed by ultimately a liquefaction flow failure. Whereas on the dynamic liquefaction front, you can have direct liquefaction first. In other words, the seismic event targets the saturated overflow tailings material where it is, and causes it to go to a residual strength state, and that then the outer wall can't contain that liquefied material, and so it bursts essentially. So those are the two or the distinctions between static and dynamic liquefaction. So the new SANS 10286, although it's still in draft, I understand that the document will shortly go out for public comment, and if there aren't significant public comments, it would be formalized in a state very similar to present. That document basically sets up a framework for assessment, which we are already using to assess stabilities of tailings dams, and this is more or less the flow that follows. So the drained analysis is the first step and defines the safety level that prevails in the absence of a trigger. So normal steady state scenario. As long as this is sufficiently high, the system does not move and it does not mobilize undrained shear strengths. Here, the target for the factor of safety is 1.5. And if you have that, you're okay. However, if your factor of safety is smaller than 1.5, then the code does make provision for you to check for the probability of failure. And there are many references that can be used. KK Foon has done a lot of work on reliability-based design. If you don't have a large standard deviation around your mean in terms of your material strengths and so on, you can have a factor of safety slightly below 1.5, and you can still have very good reliability. So very small probability of failure because of the predictableness of your materials. So that's the first drained assessment. Then the stability analyst or the designer must move to consider the peak undrained analysis as the second step. And that defines the factor of safety that prevails in the presence of a trigger. And by applying undrained shear strength properties in the model, we assume that the material is at peak undrained strength state. So remember, we're still talking about the simplistic or old school stability analysis approach here. So we are assuming material parameters. So for this peak undrained state, we assume that all of our saturated contractive material is at the peak undrained or in the peak undrained condition there. We require a factor of safety of 1.3. This is not normally a problem even for our upstream dams to obtain 1.3 for that. However, again, SANS 10286 does make provision for assessment of probability of triggering if you don't quite meet that 1.3. However, I believe that 1.3 should be targeted. All right, and then the final step of the analysis, and this is really the focus, involves assessing the factor of safety if residual undrained strengths occur. And here, a factor of safety requirement of 1.1 is proposed. And if this factor of safety is found, if the factor of safety for this assumed strength condition, again, in my diagram, I've shown we are blanketly assuming that we have a residual undrained strength condition prevailing in our tailings dam. If your factor of safety is more than 1.1, you're okay for that, according to the code. However, if you're below that, a further assessment may be undertaken to demonstrate that the probability of liquefaction is low enough. And that really is the triggering analysis that we've are hosting this webinar to address. All right, and so to address or to test for triggering, instead of assuming residual undrained strength conditions, we need two things really. We need to employ the critical state soil mechanics constitutive model, and we need to use suitable software and analytical techniques, namely finite element or finite difference analysis. The old school limit equilibrium methods, or LEM, aren't able to fully consider the required constitutive models for triggering assessments. So let's take a look at this critical state framework. So the PQ stress space might be familiar to you. On the vertical axis, we have the shear or deviatoric stress, and on the horizontal axis, we have the mean effective stress. And that might be familiar to you because that's where that's the stress space on which we normally plot the Moore circles and the failure envelope. Essentially, the critical state framework adds a third dimension to the constitutive model to introduce density or void ratio. The two are interchangeable there. So we go from a two-dimensional constitutive model, only suitable for simplistic analyses with assumed strength conditions, to an advanced critical state framework, which is able to consider changes in density and void ratio. All right, so essentially, if you were to take a group of samples and you test them at different void ratios and in drained and undrained load scenarios, and you plot their failure points in 3D space, you would see a series or a band of points, something like what I've shown on my slide here. These points basically align to form a failure line. And this is what we call the critical state line, critical state locus, the CSL. Quite a buzzword nowadays. I'm sure you have heard about it. And then to simplify visualization of behaviors, we tend to simplify this 3D model into two 2D viewing planes. So we'll frequently look at the QP plane. As I mentioned, that's the one where you have your Moore circles conventionally plotted. And then we also look at the PE plane, which we'll take a closer look at in some of the upcoming slides. So let's take a look at how some of these loose versus dense, drained versus undrained materials behave in this critical state framework. So we can start by taking a look at loose, undrained shear. So it's loose, which means we must be starting with quite a high void ratio. Your volume of voids versus your volume of solids is quite high. So we're here. And then we shear that sample, or let's say the element in the tailings dam is sheared. Because that shear is happening in an undrained fashion, there's no change along the void ratio axis. It has to stay at one void ratio value. Otherwise, it would be drained, not undrained. And if you shear that sample to failure, it basically comes up and fails on the critical state line. So having a quick look at the projections there, on a QP space, that's our typical leftward curving stress path that we know to be a contractive material. Having a look in EP space, we note a straight line moving to and failing on the critical state line without a change in void ratio. All right. The model can obviously also handle dense behavior, so dense undrained behavior in this case. So now, as I've mentioned, it's denser, so we start with a much smaller void ratio. And instead of contracting, this material, when looking at the QP plane, actually dilates up to failure. And looking at the floor of the 3D model at the EP space, again, we can't change void ratio, but we come from the other side of the critical state line and experience failure on the critical state line. Then we can look at our two drained scenarios. I won't, for time reasons, talk too much on them, but basically, because it's drained, volume can change. So our loose sample densifies and fails on the critical state line when looking at the floor of this plot. And when looking at QP space, we have a straight line stress path, which moves up and fails on the projection of the critical state line. A dense sample obviously again starts with a smaller void ratio, and also moves to fail on the critical state line, and it would follow a similar 1 in 3 gradient straight line on the QP space. Right, so that's sort of a summary of the 3D model that we're using. And just to emphasize again, when using a critical state framework, it's not necessary to assume one of the 3 predefined material states, but rather you're able to model the movement and the movement in this 3D stress space with development of the facility and with triggers. All right. I believe I've just inadvertently covered those points. So I'll move over them. You might be a lot more familiar with this plot. So this is now looking at the floor of the critical state framework with void ratio on the vertical axis and mean effective stress on the horizontal axis. So we have our critical state line dividing that space. As I've mentioned, the loose drained materials are going to fail from right to left onto the critical state line. Your loose drained materials will fail as shown there by the gray arrow. Your dense undrained materials fail the other way onto the critical state line because they initially start dense of critical, not loose of critical. And then your dense drained failure also is allowed a volume change and generally moves upwards onto the critical state line. So in any element within a tailings facility can be placed either above or below the critical state line. If its void ratio in situ places it above the critical state line, then it has what we would term a positive state parameter, and we would say it's contractive. If the in situ state of an element in a tailings dam sits below the projection of the critical state line, we would say it's dilative and it has a negative state parameter, and it's not prone to liquefaction as the contractive materials are. Okay, so then we can move to take with the constitutive models understood. I hope everyone did understand it. If you haven't had experience with it before, it can be a bit much to take in, but if you sit and have a look at some of these plots, they do start to make logical sense. But with an understanding of the constitutive models in place, we can look at the analytical methods and software. So when conducting a triggering assessment, you need to make use of a finite difference or a finite element numerical method. As I've mentioned, using LEM is not good enough. The finite difference or finite element method discretizes your soil mass into a finite number of elements, and then it applies equilibrium and compatibility equations between the elements and iteratively solves towards convergence. You obviously need sophisticated inputs for a sophisticated analysis. They say if you're going to guess the inputs, you may as well just guess the answer, and that's completely true. So in terms of material properties, you're going to need a good understanding of strength, stiffness, and density. Katie is going to take us through some of the forms of investigation and talk through how we derive these parameters. But just know that these properties influence how the elements deform and or resist deformation under different loading conditions within the bounds of the selected constitutive model, and that the material parameters are specific to the constitutive model that you're planning to use. So far, I've just talked about a critical state framework, but there are different models within the critical state framework, for example, CAM, Clay, or PM4, NORSAND, and they each have some nuances and differences there with regards to the input parameters. So once you've understood your parameters and your modeling and you've actually computed your models, you would look at your outputs. Katie's going to show us some nice examples of outputs, but just note that your outputs are numerous and you can look at stresses, strains, and displacements. So in short, the result when using a critical state finite difference software is a more realistic model of the ongoing development behavior or upset conditions of a tailings dam. This approach calibrates well with actual TSF performance under recorded historic loads, where an undrained residual strength assumption would have otherwise indicated failure. All right, so that's it from my part. At this stage, I would like to hand over to Katie, and she's going to talk to us about how to derive your inputs and what the actual analytical process involves. Thanks, Katie. Over to you.
Thanks, Thomas. All right, I'm just going to, there we go. Okay, I'll be going through the life cycle of triggering assessments, as Thomas just briefly mentioned. And that life cycle would be firstly to conduct a site investigation, which would include the collection of samples, followed by lab testing using the samples collected during the investigation, and then interpretation of the testing, calibration of constitutive models, and then developing other inputs for the analysis. So all 5 of those points would be done for the purpose of developing the inputs for the actual analysis, which Thomas has mentioned will be a non-linear deformation analysis, and it will utilize critical state soil mechanics for the potentially liquefiable material zones. And then lastly, interpretation of the results. So in the upcoming slides, I'll be going through each of these points individually. Let's start off with the site investigation. So one of the most important components of the site investigation is cone penetration testing, which gives you a very good indication of the state of your tailings. So it'll give you can empirically derive the void ratio and state parameter of the tailings. The testing also includes pore pressure dissipation tests, which allows you to calculate your at-rest pore pressures. And then the testing, CPTU testing, also has a seismic cone, where seismic cone tests are conducted to derive your small strain shear stiffness, so that you can develop a stiffness profile with depth throughout the tailings dam. Rotary core drilling is also commonly conducted, which will allow for the collection of undisturbed samples in the tailings dam. Quite often the rotary core drilling is advanced through the tailings dam and down into the foundation, which allows for collection of foundation samples, and then also for testing like SPT testing in the foundation to give an indication of stiffness. Shear vein testing is a really good way of directly deriving peak and residual undrained strength of tailings. And then lastly, the site investigation, but very importantly, will involve the collection of samples, which will then be submitted for lab testing. So it should be noted that the contractor that conducts the site investigation is responsible for actually doing the work on site and recording the data, but they do not interpret the results, and it is the responsibility of the engineer to do this and to specify where tests are required and would provide the most meaningful output. Okay, so moving on to lab tests. We commonly conduct foundation indicator tests, triaxial tests, which could either be drained or undrained, slurry consolidometers, flexible wall permeability tests, monotonic direct simple shear or MDSS tests, and cyclic direct simple shear or CDSS tests. With all of these tests, you can fully define a material's behavior in terms of consolidation, permeability, and strength. So once again, it should be noted that the lab merely conducts the lab test and records the data. They do not provide the interpretation, because this is the responsibility of the engineer, who specifies what tests should be conducted and then interprets the results once they are complete. All right, let's go through the interpretation of some lab tests. This is not in terms of the critical state framework that I'll be going through in some of the upcoming slides. This is just general lab test interpretations. So this plot that's showing on the top left of the slide is a plot of hydraulic conductivity versus void ratio that is obtained through flexible wall permeability tests. So each of these discrete points is a separate test, and the different colors represent different material types. And typically what we would do is we would use these test results to derive trends of permeability versus void ratio in this instance, as shown by, for example, the red line plotted through these dark red points for the overflow material in this instance. And we would then use these relationships or trends as input into our analyses. The second plot is a derivation of Mohr-Coulomb shear strength parameters using the Mohr-Coulomb circles with the failure envelope drawn tangential, and a friction angle of 31.9 and cohesion of 0 were derived. And then lastly, these are the outputs of some CDSS tests conducted on two different material types. So the one is red and the one is orange. And as would be expected, the cyclic stress ratio, which is the aggressiveness of the shear or the amount of shear applied to the sample, we see that as the CSR increases, the number of cycles to failure on the sample decreases. Let's move on to the calibration of the critical state constitutive models. We make use of two CSSM constitutive models, the one being NORSAND, which we use for the potential static triggers or static stability assessments, and then PM4 SILT is used for dynamic or seismic potential triggers. The NORSAND model requires 8 main input parameters. The PM4 SILT model requires 6 input parameters. So they are fairly complex models when compared to, for example, the Mohr-Coulomb model, which only requires 2. And it should also be noted that especially the PM4 SILT model actually involves a whole bunch of other secondary parameters that are either usually left as default or are inherently calculated or calibrated within the software package that you use. Okay, so one of the most interesting ways and a good way of calibrating these constitutive models is to use the lab tests that we've discussed. So this is a photograph of a consolidated undrained triaxial test, with the photograph on the left being the specimen before the test and the photograph on the right being after the test. So you can, that's basically a saturated cylinder of soil with an axial load applied until failure occurs. So we have various output plots or data from this test, and our aim in calibrating the constitutive model would be to actually simulate this test in the finite difference software and adjust the input parameters to the constitutive model so that we get the simulation to match the real life data as close as possible. Take note that I say as close as possible. We'll never get 100% fit. We are dealing with, we're trying to match up two methods or two ideas that each have their limitations and errors in themselves. All right, so this is then a simulation of a saturated, consolidated, undrained triaxial. On the top left, we have your deviatoric stress versus axial strain. And then bottom left, we have our QP space in the critical state framework, as Thomas showed a couple of these plots earlier on. So we're dealing with contraction and strain softening. The black line is the critical state line. And then this is the EP projection, once again, critical state line, and this loose, contractive, undrained stress path moving horizontally and to the left until it fails. So these green dashed lines is actual test data, and I'll play this video now. The green line that will overlay the current plots is the simulation data. So what we would like to do in this simulation is adjust the input parameters until we get the two to match as close as possible. You can see in this top left plot, we've fairly closely matched the peak strength and the residual strength, as well as the QP stress path and EP stress path. Another simulation that we perform is for the MDSS tests. Here, instead of the cylindrical soil sample being compressed axially, it is now sheared horizontally. And this is a simulation of two tests. So we've got one test which was consolidated to 300 kPa, and then another that was consolidated to 100 kPa. And there is the actual simulation. So in this instance, for the 300 kPa sample, you can see we're matching the peak strengths really well, and then conservatively underestimating residual. Once again, we're not going to be able to get 100% fit, but we want to match the behavior that's most important for the purpose that we are using this calibration for. And in this instance, yes, we did end up with a slight underestimation of residual strength, but our peak strengths matched really well. The last calibration simulation that I'll show is for a cyclic direct simple shear test. So this test is done to calibrate the dynamic softening parameters for the constitutive models. And basically there are a range of CDSS tests that are conducted at different vertical effective stresses and different CSRs, so stress ratios. And we would then calibrate these softening parameters to be applicable over a range of conditions. Let me play that. You can see that the shear strains match up pretty well as the number of cycles required to fail the sample. So we've now derived all of the parameters that we need to inform these constitutive models, and we need to assign them to the actual model of the facility to conduct the triggering assessment. Some of the parameters are not constant parameters. They may be variable depending on for example, the state parameter or void ratio of the tailings. So what we have here on the top left is a model. It's a plane strain 2-dimensional cross-section taken through a tailings dam. And the potentially liquefiable contractive zone has got shows variable state parameters. Take note that they are mostly positive, so we are dealing with a contractive and potentially liquefiable soil. And you may be asking, why is it not just a constant state parameter throughout this contractive zone? And that's because we've developed this model using staged construction and introduced a stress history into the tailings dam, and that's why there are variable state parameters. So the higher the state parameter, i.e. the red zones, are more contractive than the green. And then based on these state parameter values, the residual undrained strength ratio, which is an input parameter to the PM4 silt model, is calculated and assigned to each of the zones in the model individually. We also need to consider that we are not just we've sort of covered the calibration of the potentially liquefiable tailings, but there's many other inputs to an assessment such as this, including the foundation profile, where we would have to derive strength, stiffness, density parameters for each of the individual foundation profile layers. This could involve a process as complex as that for the tailings, especially if some of the foundation material is potentially liquefiable. Another really important input into specifically the seismic triggering assessment is the dynamic loading that's applied to the model, and this is obtained from a site-specific probabilistic seismic hazard assessment. And the outputs of that, as I mentioned, are then used to develop a dynamic time history signal. So this is a plot, an example plot of a history with acceleration on the y-axis and time on the x-axis. So this dynamic load is then applied to the base of the model to simulate an earthquake, and then we would assess the state of the tailings during the seismic event. So the time history signal is scaled to represent an earthquake with a specific return period. In this case, it was a 1 in 10,000 year return period. That return period is selected based on the consequence classification of the facility, which is a requirement of both GISTM and the SANS document. So when we actually perform the analysis, we have to develop different potential triggers and impose them on the model and look at how this affects the tailings dam. So there's different triggers we can look at, and they are divided into two categories. They are static triggers and dynamic triggers. Some examples of static triggers would be normal development of the facility. If the facility is developed too high or too fast for excess pore waters to dissipate, this could be a potential trigger for static liquefaction. Raising of the phreatic surface in a blocked drain scenario is another one. Loss of confinement, which could occur through, let's say, the mechanical removal of the toe of a facility is another potential static liquefaction trigger. And then we move on to the dynamic triggers, and these are divided into two classes. There's natural seismic events, which are essentially tectonic earthquakes, and then there are also anthropogenic seismic events, which are man-made events brought on by underground mining or surface blasting. So this is a video of a simulation of underground blasting where our client wanted to mine a reef that was underlying a tailings dam. The tailings dam is over here. And this is a potential dynamic liquefaction trigger that we looked at. the contour plot that you're seeing here on the slide is an acceleration contour plot. So if I play that video, you can see the accelerations emanating from the blast source up into the tailings dam. So unlike the sort of conventional stability assessments conducted to date, where the output of the assessment would be a factor of safety, for these critical state triggering assessments, that's not really a possibility. And so what we prefer to look at is the stress state of the tailings dam. And we do that by looking at discrete points within the tailings dams. Each of these red dots is queried during the triggering assessment, and we assess the stress state in PQE space during that potential trigger. So for example, this is an example of normal development of the facility. We've got QPE, 3D space with our critical state lines shown in the 3D space as well as in our two projections. And then we've got these blue lines represent the stress development during normal development of the facility for each of the queried points in the model. So you can see that Q and P increase during development and E decreases as development occurs, the tailings densifies and the void ratio therefore decreases. We can also look at this, and it's generally a lot simpler to look at this in two projections, our QP projection and our EP projection, as shown over here. So for this simulation, we were dealing with two different types of potentially liquefiable material, and that's why there are two critical state lines. But this family of curves has got this critical state line, and this family has got that critical state line. And generally, what we can see is that during stage construction, the P and Q increase and sort of curve upwards, but nothing intercepts the critical state lines. And the same can be said for EP space, where it starts off here at the top and then moves down and to the right. Now what we can do is, with the facility developed to final height, we can impose an additional trigger. And in this case, I'm going to show you what would happen in a seismic event. So these bold squiggles really are stress paths during the dynamic event, and we can see that the deviator or shear stress really moves up and down, and there is a slight reduction in mean effective stress, but nothing comes close to intercepting the critical state line. In the EP space, we can see that the stress paths induced by the seismic event result in movement, a horizontal trend to the left. Our mean effective stress is decreasing and the paths are moving towards the critical state line. What's nice to see is that the paths are horizontal, indicating constant void ratio, and therefore this verifies that the model is indeed being analyzed in an undrained load case. So none of these stress paths actually intersect the critical state line, and we can look at other results as well. There's plots of horizontal displacement and vertical displacement at the end of the seismic event or the potential trigger. These are plots of acceleration, velocity, and displacement throughout the seismic event. You can see that there's a permanent displacement of around 100 mils in the tailings dam, but nothing to cause alarm. If we were to look at a seismic event with a higher magnitude, we could actually induce failure, and that's what's shown by these stress paths, where multiple stress paths actually come down and intercept the critical state line in both PQ and EP projection. And when we look at those plots of horizontal displacement, there's a clear circular slip failure that's formed. And looking specifically at the displacement, we can see that it really exponentially deviates from the x-axis at around 27 seconds of the 35-second signal. Right, so to conclude the presentation, very few tailings dams in South Africa will meet the residual strength requirement laid out in SANS 10286 Code of Practice and in the GISTM. The SANS Code of Practice does, however, make allowance for assessment into the probability of liquefaction, and in this presentation, a means of assessing the potential or probability of liquefaction through a triggering assessment is demonstrated. The triggering assessment methodology allows the analyst to assess the likelihood of inducing static or dynamic liquefaction by imposing potential triggering mechanisms on the tailings dam. The key to assessing the soundness of this rational engineering approach is to verify the accuracy and representativeness of the analytical method and modeling, as well as to consider all credible triggers. The stability assessment of tailings dams requires a high level of information and skill to produce reliable results on a case-specific basis. And that's it. Thank you very much. Are there any questions?
Thank you so much, Beric, Thomas, and Katie. That was a really informative session, and I think it's very valuable to our entire audience. And I'd just like to also thank Erica for giving you guys the time to do this presentation. Yes, we will open the floor for some questions. I see in the chat we have a question from Alan Chimoli. If you have any additional questions, you may raise your hand and then I will address them after the chat question. So I don't know if any of you have read this question yet and would like to address it, or should I read it now?
Can you please read it?
Okay. So to Beric, Thomas, and Katie, excellent presentations. Thank you very much. As number one, assume that a tailings storage facility has 4 or 6 components or whatever. Number two, full well knowing that the placement of tailings is a dynamic process, etc., etc. How often, spacing and taking samples, would the engineer of record, engineer and or his or her team have samples regularly taken to carry out CSSM calculations, etc., to be reasonably confident of the factor of safety? And number three, the latter, the factor of safety is a function of time, or if not a function of time, then time interval between determination of stress states as the tailings storage facility grows or develops, etc.
Okay, good question. Thanks, Alan.
Katie, Katie, would you like me to answer some of it?
Beg you let me start, and then I'm sure that you'll definitely have lots to add afterwards. So generally what we do in terms of sampling and testing, we try to do CPTU testing once every couple of years, if not annually, to assess the state of the tailings. And that also allows us to look at if the phreatic surface in the facility is rising or if there are excess pore water pressures that have been induced for whatever reason. And then specifically in terms of the critical state testing, it is a very costly process. But what is nice about it is that we usually do, let's say, 8 triaxials to develop the critical state parameters. And then what's quite a nice thing to do is every now and again you could go and do an additional 1 or 2 triaxials and just confirm that the behavior of this new sample that you've collected it behaves in a similar manner to what you already have tested. So it's not to say that you need to go through that whole costly process again. You can just do 1 or 2 point tests and just assess the behavior. There's also an option of doing a much cheaper test, like a foundation indicator, and looking at the particle size distribution and comparing it to what you have to see if the characteristics of your material is changing as deposition progresses. Beric, do you have anything to add?
Yes, possibly. Tailings are a very uniform material compared to natural soils. I mean, it's generated in a process plant under very strict control situations there. And so the particle size distribution is being monitored on a continuous basis. The slurry density is being monitored as well. So, but in the development of a tailings facility, the key is to pay constant attention. And if something changes, then you respond. So one of the big things that can change for a tailings dam is the process engineers change the grind, because they generally trying to make finer so they can get greater recoveries. And then that can change the behavior of the tailings dam. So the key is to be in communication between the process plant who are producing the stuff and the tailings engineers that are trying to manage the disposal of it, because the one influences the other.
Thank you so much. Alan, you can just let us know if that answers your question. We have another question in the chat. It says, does the standard have a section on management techniques or best practice guidelines in the management of tailings to mitigate or prevent failure? This is from Banwa Kwanele Mongezi.
Yeah, maybe let me jump in and say yes, it has. The scope of the standard is very broad, from stability to operations. Yeah, very broad. We've obviously focused in on specifically on the stability framework, given the topic of the webinar. But yeah, if you're interested, I would encourage you to go and have a look. It is very broad and comprehensive.
If I may just add in there again, the GISTM is quite explicit in procedural conformance, compliance, and reporting, particularly heading into the public domain. But the key to a tailings dam is continual management of it, and a mine would do well to develop a specific management system for its specific facilities, and you can enhance what is actually specified in the GISTM. The GISTM is very much a check afterwards approach, whereas the tailings dam is developed on a 24/7 basis. And if you really want to manage the risk on it there, you need to do so on that 24/7 basis as well.
Thank you. Thank you. Alan, you can make your comment.
Thanks, Berik. Thanks very much. Berik, if I may chuck some stones into the pot. On some of our EXA interviews where we've had APP sort of climb the list, where we've found on the, well, being a dam engineer, interestingly enough, I've learned in the placement methods, they've changed from some mines have changed from conventional placing, and then they've come along and placed by means of hydrocyclone, which is very specialized. So obviously you're going to have different layering, but you've just pointed out it all depends on grading. But can you just expand on that, please?
Yes, sure, Alan, thank you. Look, so the disposal, it's another whole webinar in itself, is the different types of tailings disposal methods that one can use, and what people term as conventional, which is a very poor choice of terms really, is the traditional manner in which gold tailings dams were developed, and they called paddock dams or day wall dams, and they're very unique and specific to South Africa on a couple of bases, to do with the ground and the uniform grading from our deep underground hard rock mines. And secondly, it's possible because of our climate, where evaporation exceeds rainfall by a factor of 2 to 3. And then but if you go to different mining minerals like the platinum or copper, where the particle size distribution is much coarser, and it becomes a more well-graded tailings or material, they use a system called spigoting, which provides a different type of tailings dams there. And both of those, well, the Daywall Dam originated 120 years ago with the origin of our gold mining, and the spigoting method really came from those with the later development of the platinum mines. But in both of them require or rely on desiccation through evaporation, and they have to be built at a relatively low rate of rise. And when you start to have mines with very high production rates, particularly in the remining of tailings, where you're generally processing at 10 times the rate of an underground mine, if you had to try and build a tailings dam with a day wall or a spigoted dam, you would need tailings dams 10 times the size of what we currently see. So in order to, and there's never enough space or land available to do that. So we had to develop different ways or a different approach, and that is to use a hydrocyclone, which then classifies the tailings dam into a coarse fraction and a fine fraction. And the coarse fraction can be used to build because it consolidates, because it's dewatered to a large extent. You can build the containment wall at a much higher rate of rise, and therefore you can have a smaller footprint area, and you get greater water recovery out of it as well. But and that development of upstream cyclone dams is essentially the subject matter of what this webinar has actually been about, because whilst you create a superior underflow material with which to build the wall, you also create an inferior overflow material, which is what you are trying to contain. And in the upstream development of a dam, the failure surface actually goes through that inferior material, and so is particularly pertinent to make sure you rigorously understand the behavior of it, of that. So I don't know.
Thanks, Berik, for the excellent explanation. Maybe Ashley can arrange the whole webinar, or the webinar you said it might take, to give us more on this. Anyway, thanks very much for the explanation.
A pleasure, Alan.
Thank you so much. We have another question from Amam Mbweni. So he's saying, good afternoon and thank you for the presentation. Given that the finite element modeling relies on integrity of input parameters, how do you deal with the fact that most of the parameters are difficult to obtain? Example, difficulty in obtaining good quality undistributed samples.
I think that the lab test samples that we, so the lab testing is conducted on reconstituted samples. It is really, really difficult to actually get undisturbed samples from a tailings dam. So all of the lab testing is conducted on reconstituted samples. And then what we generally do to confirm that the lab test results are sort of representative of what would happen in the tailings dam is we use the CPTU testing to verify, with the CPTU testing actually being an in situ test with in situ measurements, we calibrate the two to each other.
If I can just add to your thing there, Katie. So the beauty of this critical state soil mechanics constitutive model is also that all soil samples, irrespective of how they're reconstituted, fail on the critical state line. So once you've established that line through testing of samples that are either loose or dense, then you understand the three-dimensional failure characteristics or failure line that any, that will be attained from any point of origin. So with that, you're able to model accurately. And as Katie said, the whole process revolves around verification, verifying every step along the way. So once you've established your critical state soil mechanics properties, you go and construct a finite element model in stages, and that develops a stress history, which you can then query and interrogate. And you can compare that to the actual stress state in the tailings dam, which you can get at the current time from CPTU testing. So yeah, rubbish in, rubbish out. We need to be very much aware of that. and therefore constant cross-checking and cross-verification is compulsory.
Thank you. I'm going to just ask the last question, and then we will wrap up. So we have a question from Christina Winkler, and she's saying, please comment on the instability line with your assessment of triggering, and also on undrained behavior in partially saturated soils.
All right, so the instability locus is something that we haven't indicated on these figures, but I can go over here. There we go. All right, so the instability, okay, so as I've mentioned, this is the critical state line. This is where critical state conditions are reached. The instability locus is a line, a theoretical line through which instability or liquefaction would occur. And in this case, I suppose you could sort of see it, it would be where this point starts to trend downwards and there's a loss in strength. And if we were to connect the peaks of all of these paths, we would derive an instability locus, which would be the stress combination at which liquefaction would occur. So yeah, that would be the comment on the instability locus. And what was the second one?
I was asking about undrained behavior in partially saturated soils.
Oh, okay, yes. So there is the potential for unsaturated material to behave in an undrained manner if the degree of saturation is above 80%. And so typically what we would do is we would be really conservative in where we would apply these undrained conditions and the phreatic surface and saturated conditions in the model to ensure that a sufficient amount of contractive material behaved in an undrained manner.
All right, thank you. I don't know if we have one last question. Okay, from Adrian Mankis is saying, good afternoon and thank you for the presentation. How do you deal with CPTU screening methods and parameter interpretation, and considering how to integrate other fields and laboratory testing into the CPTU interpretation results, such as obtaining profiles of void ratio with depth and the problems to obtain such samples?
Sure, that's a broad question.
Okay, maybe just
so,
a summary.
Yeah, look, there are obviously various empirical methods. So a CPTU test does not allow for a direct calculation of many of these parameters like void ratio or state parameter or even undrained strength. And there are many different empirical methods that are used to derive these parameters, and specifically undrained strength. We typically use Olsen and Stark or the NKT method to derive peak undrained strength, and then the Jeffries and Bean prescribed method for residual undrained strength, where they use a bunch of case histories to derive an equation to calculate your residual undrained strength. But what is really, really valuable, because as I've said, these are empirical methods, is to actually conduct shear vein testing on the tailings dam. And this allows for a direct calculation of your undrained peak and residual strength. And then you can verify or decide which of these empirical methods actually matches to that direct measurement best and go with that.
Okay. Thank you so much. Just once again, thank you so much for coming. We really appreciate your willingness to answer all the questions and for your very thorough presentations. And thank you to everyone who attended. It really makes it worth it for our presenters to come out and present to. We had at our peak about 98 people watching, so that's really amazing, and we thank you for that. I want to just spend 2 minutes advertising a bit for SANCOLD. So if you are not a SANCOLD member, you can go to our SANCOLD website and click on the Become a Member button and you can join us. This is very helpful in terms of registering for EXA, or if you are already registered for your voluntary association requirement, and it's one of the most affordable groups to be part of. So please do that. And then we have the SANCOLD short courses that on slope stability, specifically for tailings dams. That's coming up just before our conference in November, 4th to 5th November at the Wanderers Club. And you can also go and look at our website for more details on that. And then, of course, we have our conference coming up from the 6th to 8th November, also at the Wanderers Club. And our registrations are only open on the 2nd of September. So we'll send more information on our LinkedIn page when that becomes active. So thank you all for coming today, and I hope you have a good evening further.
Thank you. Thanks, Ashley.
Thank you.